So, hey everybody, thanks for coming. If you came to hear a talk about software correctness in some form, then this is the right room. So, who in here is like 100% happy with their software stability or like its speed? Either what you build or what you use? Hopefully no one. I think we can do a lot better than we do right now. So I want a world with better software. And if you want something to happen, you should take action. And so like if I wanted apples, I'd plant a seed or nurture a tree so I could get as many apples as I want. So this talk is me planting a seed. I want better software. So the purpose is to convince you to care about building better software or building software better. And once you care about that, I think that we will get better software. But who gives a crap, right? Why should you care at all about any of this? Like, we go to work, we get paid, we buy donuts. And if this doesn't change that dynamic, like, what's in it for me? Well, this is what you spend your life doing. We all die eventually. So sorry to kick off the talk with morbidity, but if it makes you feel better, there's more to come. So wouldn't you like your time on Earth to be spent doing something that makes an impact in a positive way? Software is the biggest lever the world's ever seen. I like using this picture for sort of this analogy. So using this software as a big old lever metaphor, the best thing to do to have more impact with our software would be like to extend the lever, right? Because you get more leverage. And so that's kind of what computer science researchers do. So they, every time they come up with something novel, we get a little bit of the lever. But I think it's sad, but it's basically unimportant that they do that right now. And the reason for that is nobody's at the end of the lever right now. Most of the industry, at least, is sitting very close to the fulcrum and like pushing. And when they want more done, they push harder. They get more bodies to come to push harder. But like you can just move down the lever to have more impact. So anyway, I think often I see people get frustrated by software being hard, but they don't. Like I can tell them, hey, you can move down the lever by doing this or that, and they just kind of don't care because it's not how I do stuff. Anyway, so the good thing for you is if you want to like beat them, you can move down the lever and beat people that are still doing stuff dumb ways. So we'll come back to sort of that a little bit, but let's talk about where things are today. So what does it mean to be successful with your software company? If your software is useful, I assume that some people use that software. Hopefully, a lot of people use that software because most business models not developed by the Wu-Tang Clan revolve around convincing a large number of people to use your product. So let's assume you're working on really successful software and do some math. So you have 10 million users. This is pretty good. That's a decent number. To get the value out of the software that they need, they visit, on average, say, 10 pages per day. I think this is an unusually low number if you have useful software, but so that means I think that this is a conservative estimate. But you didn't build your software very well. So each page load, let's say, takes on average 6 seconds. We probably don't have any software extant in the world that has long load times and that you wait on regularly, right? Not banks or other financial software that have massive, basically everybody has to deal with one of these. Or like the dashboard of what is maybe the biggest modern hosting platform that people care about, at least one of. Okay, so 10 million users visiting 10 pages per day that each takes 6 seconds to load. Turns out that's 10 million minutes a day. It's not an easy number to wrap your head around. 10 million's big, and we don't handle big numbers well, so I wanted to break it down. So it's 166,666 hours per day, or 6,944 days per day, which is not a unit that I actually deal in very often, or 19 years per day. So that's 19 years a day spent looking at a loading screen. That's a lot of time, but who cares, right? We're making money, we're buying the donuts, and everything's good. On an unrelated note, the average human lifespan is 80 years. So congratulations, your software kills a human every 4 days. And it's software, so it doesn't ever sleep in its bloodlust. So I'd like to propose that our metrics dashboards maybe should track a mortality rate based on load time, right alongside our other metrics to kind of drill this into your head. I think it's kind of important, but people don't care about it. But why do I bring it up? To convince you that you have an obligation to do your job well. If you aren't great at it, but you write successful software that people use, you're basically more efficient at snuffing out human life than the most effective serial killers the world's seen. So I found this comic from Saturday Morning Breakfast Cereal pretty relevant. It says, your theorem on diffeomorphic function construction, I found a way to use it to cure cancer, with the caption, fun time activity, forcibly converting pure mathematicians into applied mathematicians. So think of the person in the background as me, and my math earlier as the thing that makes you cry at night as you come to grips with your obligation. So this leads me into the point of the talk. Should we be worried about getting things done now or right? This is the trade-off at the heart of this tension between expediency and correctness. With that in mind, let's talk about object-oriented programming versus functional programming. I'll talk about my transition personally, just sort of to, I don't know, personalize the situation. So this is a language, Ruby, that's near and dear to my heart. I learned about Ruby with Rails, so like that was when I became aware of it. It was before Rails 1.0 came out. It was in the comment section of some Slashdot article. I've looked for it. I haven't been able to find it, but I do remember that's the case. So that people don't think that I'm saying Ruby is awful in this talk, since I am sort of not bashing OOP, but suggesting a transition. Understand, I really love this language. Before Ruby, I was not developing software in an expedient manner, and I wasn't building correct software. So Ruby introduced me to the joy of test-driven development, and this helped me make my code substantially more correct than it ever could have been before I knew about this, or sort of vaguely knew about it, but no one did it because I was in a Microsoft-dominated space at the time. It also just made me develop software much faster. But in the course of running a consultancy, building Ruby apps for a decade, some things happened. We got to build bigger and bigger software, more interesting applications, and these ultimately required various forms of concurrency and made me care about concurrency. So I continued to build the applications in Ruby, and at this point I stopped being expedient or correct with my software development practices. So things were basically awful anytime we had any scale on a concurrency-focused application, either for the end users or, if we are taking our obligation seriously, for the developers, depending on where we placed our concurrency concerns. So at this point, I felt like there were cracks in my superpowers. Before, I could build stuff that I hadn't been able to build before, and it was like fast, and people used it, and it was great. But once I got to this point, it stopped being fast. It was not pleasant. I had a lot of people tell me that functional programming is great, that's made them happy, and it would help me solve my issues. But there was a problem, and it was this. Functional programmers seemed really smart, but the ones I talked to seemed to not actually build stuff and put it out in the real world, but they really enjoyed programming. So they'd spend a lot of time seemingly just talking about how monads are food stuff, while I was building applications with real business value, and my clients were selling their companies that we built applications for 9 figures. So I had a hard time taking it seriously because no one that was telling me about this was actually building software out in the real world, seemingly, at least the ones that were close to me. But conversely, this is how functional programmers saw me. And in a large part, we were both right at the time. I think part of the reason it felt like functional programmers weren't building stuff, though, is there's not a need for things like the solid principles, right? And consequently, there were fewer smarmy blog posts with very trivial concerns that people still found interesting. Your apps are composable by default if they're made of functions. Their functions are composable. So fewer smarmy blog posts meant that when they did post, they had put out things that were very dense or confusing, seemed like a lot of work to somebody who, there were no beginner posts, right? So there's this big gap, this gulf. So I think functional programming wasn't picking up very widely. But my superpowers had broken down, and I didn't want to do functional programming at the time. So I got interested in the actor model in Ruby via Celluloid as a library. There's another sort of actor model library out as well. I forget the name of it. It was all right. It was pretty good. I could do neater stuff, and I could handle a little bit more load. If you're not familiar with the actor model, it's all about concurrent processes that live at the same time and send messages to each other and don't share memory. With the actor model, I was able to build real-time things that I couldn't have dreamed about building successfully earlier. But it still had cracks because in Ruby, at least the default implementation of Celluloid depended on basically threads, and so you could really get to 1,000 actors, but tens of thousands of actors was a no-go. And so eventually, again, as we hit scale, things got bad. I had to do things like multiplex the purpose of actors just so that they could do enough stuff that we could support the load. And at that point, I didn't really even get the benefit of it. I mean, I got sort of the benefit of actors, but I didn't get. I was not living the dream for sure. All right, so do you know who this guy is? Yeah. So he's a hero of mine. If you're not familiar with him, you owe it to yourself to look into him. He invented the concept, the phrase object-oriented programming while working on Smalltalk. So he said this about modern object-oriented programming. He said, I invented the term object-oriented programming, or object-oriented, and I can tell you that C++ was not what I had in mind. The actor model is really what he meant by object-oriented. He's confirmed this on Hacker News comment thread recently. I'm not just making it up. I find that really interesting. These things get lost in industry because people in industry basically don't care about programming history or reading about stuff. I mean, it's a broad brush, I know, but not everyone in industry, but industry as a whole is mostly concerned with, like, let's build this thing and maybe we need a factory of people to do it and move on. Anyway, so people don't care as much about programming history as maybe me. So I read everything that I could on the actor model, and if you do this, this will lead you to Erlang. I really hated that I couldn't ever seem to write my commas and semicolons in Erlang in the right spots, which on the first pass, I mean, obviously I got it. But I love the primitives that Erlang provided, and I was very, very impressed with the runtime. I'm not saying the syntax is bad, it's just, it's not necessarily beginner-friendly to at least some subset of people. A friend then sent me a talk by Jose Valim at ORDEV, and I immediately decided that I needed to look into his language, which was Elixir, and learn it. But of course, time is finite, so it took me a while. Eventually, though, I did come to Elixir, and I fell in love with it. So this talk is a little bit about Elixir, because Elixir allowed me to start writing code that was more correct than the code that I was writing in Ruby, but it still gave me the expediency of development that I got in Ruby. And so consequently, obviously, correctness and expediency aren't actually a dichotomy. You can have both. It's possible to expediently write code that is correct. So this is actually one of the draws for me to Elixir. I'm not trying to sell you on Elixir specifically in this talk. But I am suggesting there are some very serious correctness benefits that a language like this gets you that you're not really likely to achieve in practice without this kind of tool at your disposal. If you're on the .NET stack, there's F#. It'll give you a lot of the same benefits, and it seems awesome. If you end up getting to play with Orleans on the .NET stack, then I'll even be jealous of you, but probably not without that. And if you're at a Java shop, there's Scala, there's Clojure, there's Kotlin. There are other things that might fit the bill and still allow you to do the work that you're doing. But we're going to talk about Elixir for now and just discuss at a high level the parts that were important in helping me write far more correct code than I'd been doing before. So the parts that normally come up in any kind of survey of Elixir are sort of a small part I'll discuss. These are the details that bring people to the language typically, and they're important to get right. So it's a functional language. This matters a whole lot. If you have a functional language, especially a highly concurrent and fault-tolerant functional language, then you can build systems that are fast and isolated, so isolated failures that have insane uptime while keeping the code easy to reason about. Like my multiplexed actors in Ruby, they were not easy to reason about. You had to know way too much to actually figure out what was going on. And I was forced into that by constraints on kind of the fundamental, there's not a runtime really in Ruby, but the language itself. So functional languages are inherently composable. So all the work that you put into building foo widget factories and stuff, you don't do that. You just spend that focus on actually building the software that you're dealing with instead of these weird abstractions that you ultimately have to make so that you can compose object-oriented stuff. It's immutable. This is one of the most important things, right? Global mutable state is the source of all evil. It's the worst. But immutability makes things way easier. So for instance, I wrote a Tetris game in Elixir, and I have a only allow valid moves function, right? And so what I could do is I could apply the moves and then look at what the new state of the world would be and be like, should this be able to happen? And if it shouldn't, I could just throw it away. And if it should, then that becomes the new state. So this is how I handled collision detection in the game, and it was great. I was not going to be able to write that code that way in Ruby because if you're writing a Tetris game or something in Ruby, you're almost certainly mutating a bunch of objects, right? You can't really roll back easily. You can't do deep duplicates very easily, especially in Ruby. But in most OO languages, deep duplication is hard or something. Anyway, so once you mutate, it's very hard to undo and roll back. So here's the code. This is the collision detection code. I'm still dealing with state a little bit more than I'd like to, but basically you handle input, you give it the original state and the thing that happened. You get what the new state would be by deferring to this other do handle input function that knows what left arrow and right arrow mean. And then just a conditional, if the new state is valid, then cool, that's our new state. And if it's not valid, then we just return the original state. And so by doing that, any button you press that returns an invalid state just doesn't do anything because we just throw away what would have happened. If I were to model this in a language that had maybes built into the standard library, I would do it a little differently, but I still think it's pretty good. I like it. Anyway, so this is one of the reasons that immutability being first class is really important. You can, though, get immutability in almost any language. So in Ruby, there's Hamster. There are various immutable libraries for just about any language, I'm sure. And those are good, but generally they tend to not be as fast as they could be if they were first class. They definitely don't have as many users, and you have libraries that just won't work with them, right, because they expect to mutate things. Anyway, so then there's concurrency. This is why I think most of the people that I talk to come to the language. The Erlang virtual machine that Elixir runs on has concurrency like completely figured out. If you're not familiar with how the virtual machine works or how Erlang scheduler works, then you're in luck. I wholeheartedly recommend reading up on it. It's like one of the like wonders of modern software development because it's so simple but so powerful. In the meantime, here's a quick crash course, and actually I stole this slide from Brian Hunter there. Well, he gave it to me, so I don't guess it counts as stealing. But in Erlang, you have a lot of these concurrent processes that are running along. They can't block each other because of how they work. So the way that works is there's schedulers, and there's really one of these schedulers per core in general. You can tweak it. And the scheduler gives 2,000 reductions to each process in the loop by default. Again, you can tweak it. And then the scheduler handles the next process. And a reduction you can think of just being like any machine instruction. That's essentially what they are. Because they designed this way, like all of the other concurrency things fall out of it. And so this is like, this little picture is why Erlang's concurrency is amazing. They had to get this part correct. So there's an example of where you can't really defer to expediency, right? They could have built a virtual machine or a scheduler that was like faster to build or not thought through it as well. But if you do that, you don't get Erlang. You don't get what we like about the virtual machine. But it might also be an example of how expediency still is okay, kind of, because Erlang's soft real-time. It's not hard real-time. So it's conceivable that you could build something like this maybe with hard real-time properties, but I'm sure it's way harder, and that's not what Erlang did. Anyway, so I think this is fascinating. I really love it. I don't know. There's like just some aesthetic about how it was built. And when you read up on how it works, it's just very impressive. And also it's required that you don't share state for this to be sort of feasible. Anyway, I find it hard to explain why I love it so much, but just the simplicity of the design makes me feel warm like whiskey. And then fault tolerance is the other reason that people come to the virtual machine. So an Elixir application built properly just runs forever, just forever. Ericsson built a telephone switch that had 9 nines of uptime in Erlang. That's a lot of nines. It's basically unheard of. I have a small anecdote to mention here. At my consultancy, we had a client that was building real-time delivery as a service. So part of the platform involved like a WebSocket thing that would expose driver location. So drivers' phones would, update us on where they were. And then people would view a map on the web or a mobile app, and they would get WebSockets to push the data down to them. I built that piece in Elixir, like before Elixir 1.0, before Phoenix 1.0, and I literally deployed it on a screen session. Like the first time it went down, or the first time we updated it, I was going to like do a proper release and build a service and all that. But I never did. All this thing did was shuffle data and tweak some stuff and handle encryption and authentication. So it's a pretty basic service, but still. 8 months after I deployed it, the CTO called me and said, hey, just wanted to double check with you. We're shutting down these machines on Amazon and just wanted to make sure that like you don't think we need them. And this was one of them, the thing that I built. And he didn't know what it was because he had never had to deal with it because it never had a single problem ever in its history. It was still running on screen 8 months later and had never dropped anything. This was awesome. This is not my typical experience. They actually pivoted business models and didn't need this feature anymore. And so technically I'm claiming 100% uptime of the service. I feel good about this. Although I'm told that 100% uptime is also code speak for we don't do monitoring properly, so a grain of salt. Okay, so those are the reasons that people tend to come to Elixir, and they're awesome, but there are a few other really important parts of the language that don't necessarily get as much public love as they should, and I want to talk about those as well. So there's likely an equivalent to these in whatever your language of choice is, whether it's OO or not. Now I'd like to talk about the features that help you ratchet up the correctness of your software. So there's DIALYZER. If you're unfamiliar, it lets you do what's called success typing. This isn't as strong as like a Hindley-Milner type system, but it's way better than not having type checks in your software. The sweet spot is that you can build software without spending time specifying types or really you just throw together a prototype, whatever. And then later you can come back and you can add some sort of type declarations on top of it and let DIALYZER run over your code, and it'll say, turns out you said that this thing could return only positive numbers, and I found a -1 or whatever. Turns out that this has to handle all negative numbers, and there's this one particular case it doesn't handle, or whatever. So with Ruby and Friends, there's no way to do this really reasonably. Your language might have something like this. If it does, I recommend you start using it, because you'll find your bugs before they hit production. Like find them at compile time or in your continuous integration server rather than finding them in your bug tracker. For JavaScript, there's Flow.js. I'll talk about it briefly later. If you write JavaScript, you should use Flow.js. So what benefits do you get from a tool like this? Yeah, I mentioned it. You can find case statements that don't cover all their cases. Sort of like just general stuff that you should handle, and we often don't. Okay, then there's QUICKCHECK. So it's a property-based testing tool, and property-based tests are amazing. They let you write code that will write tests that will verify code based on properties it should have. So for instance, you could specify some property that a particular function should have, like this thing should act like the native array module, or for all of the integers, squaring the integer the square of the integer is greater than the absolute value, greater than or equal to the absolute value of the integer. They then generate the equivalent of hundreds or thousands or hundreds of thousands of unit tests for you, depending on how you configure them. And so this is another example of a tool that lets you bolt on correctness after the fact. What's amazing about it is that once it's found a property failure, maybe you have a state machine that through some weird thing gets into a state it shouldn't get into, it will do something called shrinking. So it'll reduce down to just the smallest number of steps it could find that led to the same bug, and then that's what it gives you. And so you can see, like, do this, 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 and this, and you hit an invalid state. So I've got a video that's linked in my slides that I'll put up somewhere, I guess, that has John Hughes actually talking at NDC 2013 about how they built a QUICKCHECK harness for Volvo, and it found bugs in basically everybody's implementation of the protocols where messages go around inside of your vehicle. So if you like not having people run over you because of software bugs, like, there's some thank to be given to QUICKCHECK, and I'll give you a fun case about this. So one of the nastier bugs that he found, he actually goes into detail in the video, is higher priority messages. So like when you're building these things that go over the CAN bus, you specify like this is high priority, this is low priority, and obviously the high priority messages should come first. But there was one vendor where, because of an intricacy, some low priority messages could go on the bus before the high priority messages, which, you know, sounds like, okay, what do I care? Well, among other things, imagine that you have a lot of low priority messages like, hey, turn up the volume by a little bit. And you have a high priority message, which is like, apply the brakes, if you have drive-by-wire brakes. The low priority messages would get processed before your high priority message. So realize this, the consequence of this is an edge case where, like, when you want to turn up your jams, you might actually just not be able to brake and squish that lady with the stroller. Anyway, so back around to the morbidity and the obligation to get things right. That is a thing that could happen if you write bad software. But enough about manslaughter, let's talk about tracing. So it turns out that you'll eventually want to figure out what's happening in production. And if you're using the Erlang VM, they're great, great, great tools to check this sort of thing out. If you're doing Elixir or Erlang, there's this tool called ERLYBERLY that's really cool. It's a Java application that connects to Erlang network, and you can just do tracing and other things. So if you want to play with tracing, it's a good starting point. The interesting thing about tracing in Elixir or Erlang is you can hook into a production system and you can just find out about calls to a particular function or to a particular function when the third argument is 7, or, you know, anything else really you can think about doing. And this is good because doing tracing, like, lowers the throughput of your application, right? It's doing more stuff. So it's nice to not just like get a log of everything that happens and being able to filter very, very tightly. The Heroku router is built in Erlang, and Fred Abair from their team talks a lot about it in a book he has called Erlang in Anger, I think. Anyway, so really cool stuff. And in Java, there's a thing called like virtual VM. It's not the same thing, but if you're writing Java and you have not played with virtual VM, you should play with it. It's great. I'm not sure about an equivalent tool on the .NET CLR. I'm sure one exists. Anyway, and then there's other just really neat stuff that people ought to talk about more, and they don't really. So there's Hype. This is the one I wanted to talk about, which is high performance Erlang. So the way this works is it compiles an Erlang module into machine code, and then that machine code is shipped. So Erlang modules are like compiled into this Beam file, which is like the virtual machine language. And it has all these parts, and one of the parts is the place where it stores the machine code. And so what you do is you have, like, it compiles the Erlang version and then the machine code version. And so they both get shipped in the same file. So that means if you if you compile with Hype and then you move to a different architecture, your app still works. The machine code part isn't being run anymore. It's back to the interpreted part. But that's very cool. It's a really neat thing. I don't know of anywhere else that does that. Anyway, so this is important in the context of expediency versus correctness because people might bring up that Erlang or Elixir are slow. And for certain workloads, they're definitely right. But Hype gives you like an escape hatch that falls short of having to just rewrite your inner loop in C. So consequently, you can still write code. You can get the guarantees from DIALYZER. You can run a QUICKCHECK on it. And then you just compile it to machine language and you get better performance. Anyway, I think that's a nice trade-off. So that's Elixir. And with Elixir, I found that I was able to build software more easily, more quickly, that was way, way, way more correct, and provably so. And when it wasn't correct, it didn't cripple everyone because of the fault tolerance. So anyway, this is a huge win. Even though Elixir is considered slow, my stateless response times dropped from like 100 milliseconds on a web server to like 4 milliseconds on average. And I know that's a very like abstract, context-free number, but just in general, like doing the same thing in, say, Rails, I had drastically like 25 times worse performance. Anyway, so that's why functional programming languages can make the backend great, but these days you end up having to have users, and that means inevitably you have to write some sort of front-end code, which often means that you have to use JavaScript. So in the expediency and correctness flow, JavaScript errs entirely on the side of expediency and says like, nah, correctness is stupid. Anyway, so that's why I brought up Facebook's flow.js. There are now some options for proving correctness on JavaScript code, and that's really good. It's nice to know that your code does what you think it does. So as I mentioned, Flow is kind of like DIALYZER for JavaScript. So if you want to move your JavaScript along more towards correctness, you should be using this. But maybe just don't write JavaScript at all, because there's this thing called Elm, and it's amazing. So it's beginner-friendly to a fault. It's really, really beginner-friendly. John Carmack said that it has the best error messages, and everyone should try to be like it. It's got a Hindley-Milner style type system. It's instantly reactive, strongly typed apps. They're very fast without a whole lot of effort. The renderer is faster than basically all the other extant frameworks for building front ends in JavaScript. It focuses really, really heavily on favoring correctness over expediency, but it's still very fast to build things. I'm faster in it than I was in React or anything else, and I've broadly considered a fairly fast developer in those languages. And it also has managed side effects, which are nice. If you care about that thing, that's a good thing. So this is a diagram of a typical Elm program, so just look at that for a little bit. You'll figure it out. Sorry. Okay, so it might seem confusing, but the important part is just you provide those green boxes. So there's like 4 functions basically that you provide that matter. And I'll kind of go through them. So the init function, this returns your application's initial model state. So like your application has some state, and then like it looks a certain way. View is like a function on the state. The update function handles incoming messages and updates your model, and could send out side effects. That's what that command type is. Those are things that, like, the commands are like, gosh, it'd be nice if somebody would make this HTTP request for me. So like they're a request for a thing, but not doing the thing, and then the runtime handles doing the things. And so everything is pure. Like all of these functions are pure. You can't write an impure function. Actually, every function has a single expression. That's all a function can be. So the type system, because that model and command separation in the output of update encourages or forces strict separation between things that change state in a pure fashion and things that ask for outside help. Anyway, so the view function just takes your model as input, and it produces, say, an interface to the user, right? Whether it be HTML, a buddy of mine made a thing that rendered, as the view, it rendered like this Quark synthesizer grid of buttons on a hardware device. So anyway, when the user interacts with the view, they can produce messages, and those messages ultimately get routed by the runtime back to your update function. So the user produces a message, that goes through update, you say what to do with that message, and then the view updates if the state changed. And then you have subscriptions, and those are just things that happen in the outside world. So you can think of this as WebSockets, right? Somebody sent me a thing, I didn't ask for it, it just happened. Or the ticking of a clock, right? That's why I have a clock down there. And then those also produce messages. And then all of those same messages get routed through the update function. This might seem complicated, but we'll see a basic program real quick. This is the stereotypical first Elm application. So here are the types. Our model is just an integer. We have 2 possible, so our message is a union type or a algebraic data type. It has 2 possible values, increment or decrement. So again, messages, literally every single thing that can happen in our application is, exists in that type. When we get a message, it ends up being provided to our update function along with the current model. So the first argument is message, the second argument is model, and the result is a model. And we have just a case statement here. It says do a case statement on the message. If I didn't handle all of the messages, this won't compile, right? So if I just forgot to say what happens in the case that somebody sends me a message that has a nil or whatever, it would be like a nothing, then I can't compile my code, and it'll tell me. But here we're saying, look, if we get an increment message, we just increment that integer that is our model. If we get a decrement message, we just decrement it by 1. You could get these same guarantees in Elixir or Erlang by using DIALYZER and specifying a type for your handle cast functions with like type specs, if those words mean anything to you, and then enforcing that DIALYZER passes in your test script. So you don't get them like, it's not like it won't compile, but you wouldn't be able to run your test successfully. All right, so then we get to our view. Our view takes the current model and produces that type HTML message. That's a parameterized type. So HTML can produce something, and the thing it can produce is our defined type of message. And so that means that we know all of the possible things that could come out of this HTML that we're rendering. And so here we just have a div. The HTML stuff basically consists of like a function that is for the type of thing, and then a list of attributes, and then a list of children. So we have no attributes on the div, and then we have children, 3 of them. We have a button. When you click it, it's decrement. It sends out a decrement message, and it's like inner containers a text node with a minus sign in it. Same thing for the plus button, although obviously with plus. And then in the middle there, we have just the model's count, the current value of the model. I should actually say model based on what I said the model was, but whatever. Model.count is not a thing. And then this is kind of how you wire stuff together. So this is a beginner program. There's 2 variants of it, but basically you say, here's my first model, here's my view, here's my update. We have no subscriptions in this application. That's the difference between like beginner program and program. Anyway, so that's it. That's how you wire everything together, and that basically, that's a data structure that you hand to the runtime, and so that it knows what to do with the messages that it gets from the view, where to send them. Anyway, so if you get one thing out of this talk, I want it to be the math at the beginning. If you get 2 things out of this talk, I want you to try Elm. If you've never felt like just joy at a type system, which maybe sounds weird, Elm will give you that, and it'll make you think about programming in a different way, potentially, if you don't already think of it this way. And it'll make you want to write more correct code. And this is the brief portion of the talk that we refer to as advertising, where I mentioned that I happen to run a startup that does daily continuing education on Elm, Elixir, React Native, Swift 3, other things, because I want to help people build software better. Anyway, so if you want to look into Elm or Elixir, I can help you. You can come talk to me later. Are there any questions so far? There's no more advertising. The talk shifts a bit moving forward, so now's like a really good time if there are questions specifically about this part. Awesome. Okay. So let's talk about computer science. Before we move on, I want to reiterate the 2 primary technical takeaways I want you to leave with, which is slow software is killing people, and you should check out Elm. But why did I decide to give this talk in the first place at all? Historically, I've given very code-focused talks that focus almost entirely on hey, I built this thing, and here's some cool stuff that came out of it, and let's talk about that. Very light on the philosophy, typically. But this is John Backus. If you don't recognize his name, you'll definitely recognize a couple of things he's known for. So the first is Fortran. In 1953, he worked at IBM. He convinced his superiors to let him build a language that made it easier to work with math equations than coding assembly directly. Fortran is an imperative language. It's been developed ever since 1953. It also now supports parallelism and object-oriented programming. This strikes me as hilarious because it did not, if you look at what it looked like originally, it's so different. Anyway, so there's one reason that you might know who he is. Here's an example of Fortran code, just so you've seen it before. It's extremely imperative. This is just a recipe. So I always call these recipes. It tells the computer what to do step by step. So it's essentially just a thin shim on top of assembly, but easier to write. He also invented what's known as the Backus normal form, or discovered, probably invented. You might hear Backus Nauer form because there's another guy that also kind of, at roughly the same time, discovered it. It's a means of defining the rules of a context-free grammar, and essentially every programming language or markup language that you know has a BNF or an eBNF definition. This is part of the BNF grammar for JSON, just so you can have some in front of you. If you read RFCs, they're littered with BNF definitions, and so John Backus is responsible for Fortran, which is one of the longest-lived, if not the longest-lived, extant programming language, and the means by which people define what their programming language is, or the grammar. So he's pretty influential. He knows what he's talking about, and here, if you're sharp, you'll notice I'm making what's known as an appeal to authority. He's also extremely familiar with imperative code, and his invention of BNF won him the 1977 Turing Award, which led to him giving a talk titled, "Can Programming Be Liberated from the von Neumann Style?" So he was so troubled by what he saw happening as a consequence of this imperative coding that everyone was doing. He took the opportunity of his most prominent speech of his life to tear imperative programming to shreds, and he does. This guy named Fred Yankowski from the Elm community is the person who linked me to this paper. I'd heard of it before, but he mentioned that it was, that it affected him pretty strongly. And so I'd heard about it, hadn't read it, so I sat down one night with a whole pot of coffee at midnight, like one will do. It was only 26 pages, so I thought it should go pretty quickly, but it took me 2 hours to digest it the first time, and since then I've read it around 10 or probably 20 at this point, more times. So it changed my life. It's a good paper if you want just to play with papers. It's not too dense. It's easy to get through with sufficient coffee. It's worth talking about a few things here before we get into the paper itself too far. So first off, what does he mean by the von Neumann style? To explain that, let me first introduce this guy. This is Alan Turing. In 1936, he came up with the universal Turing machine. This is the foundational model that all of our computers are built on. It consisted of an infinite tape and a read and write head. Out of these simple pieces, anything that we can do in a computer today, right, we can do. So the one thing you couldn't build from this model was an actual computer because we have a shortage of infinite tapes. But that's where this guy comes in. In 1945, John von Neumann described the machine that they had built to do some math for some reason or another, and this machine was an actually constructible realization of Turing's machine. It's philosophically identical to the laptops that everyone has. You program it by giving it essentially a recipe of instructions, right? That's the imperative style that we're all familiar with. That's how it works in essence. You have your input, you have a CPU, you have some memory that it's connected to. The CPU reads your input, does some stuff, maybe stores stuff in memory, and then puts stuff out the output. Oh, also, those arrows, right? Those are the bus between the CPU and the memory because it has to get data over there somehow. Anyway, back to BACKUS. Here's some code. This is written in ALGOL, which is what he developed BNF4 originally. So this is some code that he uses in his paper to make a point. If I leave it here for a bit and you look at it and squint real hard, you might figure out what it does. Does anybody know what it does? There's no way I would have figured it out in this time period. Okay, so it took me a long time to figure out. It is inner product. So it defines inner product in an imperative fashion. There are a few things that BACKUS found interesting and suboptimal about this style of coding, and so I'll just kind of list them. He said there's some invisible state, that A, that B, and that N, that don't appear here, and it's being operated over by complex rules. This is not hierarchical. It's not building up from like these basic simple operations, really, in a composed fashion. It's dynamic and repetitive, right? That for loop is the essence of repetition, right? That's what it does. You have to work through what it does in your head in order to properly understand it. You have to internally handle bookkeeping for mutating that C variable. You have to remember that that I variable is incrementing. That's not hard, right? We all learned to do it, but we all did have to learn to do it. But his biggest gripe was that it computes word at a time. Because it's mutating the state, it's modifying something in memory, right? Like, you can imagine maybe this fits in a CPU cache or whatever, but in general, like, anytime you're mutating state, you're going over that bus and putting something in memory or getting something out of memory. So, yeah, in this case, it's modifying the I and the C. And it has named arguments A, B, and N, and that means it only works on vectors of lengths N, though there's nothing that says that. You just have to know that. And only on the vectors named A and B. And granted, we could like handle these with a function call by using name parameters, but that too is assignment. And so ultimately, that means taking data out of memory into the CPU and vice versa. So let's talk about how that works. Again, this is the von Neumann machine, and that thing at the bottom is the bus. So those two arrows are what is referred to as the von Neumann bottleneck. Each bit of mutation that happens essentially moves some data across this bus from the CPU to memory, and this is slow. It's way slower than keeping computation and data on the CPU itself. Like if you have to go fetch the data, it takes time, way more time than doing the math. His complaint was that most of programming in the imperative style revolved around bookkeeping, and that meant that we were going over this all the time. And that's slow both physically and it's slow for the programmer as you think about it, or as you reason about all the data interchange, because you have to think like, you know, what was that variable name, or like if I've used that variable before, then I'm overriding it, and oops, that's going to cause a bug, but not an obvious bug. It's some insidious bug that just kind of happens later. Anyway, so my whole life I heard about the von Neumann bottleneck, but this is the paper where he coined the term, and he explicitly talks about it as also being this bottleneck for the programmer's mind. And I'd never heard anyone tell me that before, so this is why I think it's valuable to read papers, because it is. You have to spend a lot of time like learning to write code and learning to do the mutation in your head to read it successfully. And before I read the paper, I thought he was only talking about the physical bottleneck. So this is a different way to write the same inner product function. This is just some pseudocode. You can imagine that each carriage return is just compose this function with the next one. So this is a point-free notation form of inner product. So it's a pretty straightforward way to implement inner product. You kind of have to have dealt with the point-free programming style for it to be quick to read, I think. But it is small, and you can see that it's sort of composable, right? We've built up these pieces, and we compose them by composing the function. That's what it's called. And that gives us this bigger function. But what's interesting about building something this way is when you make a recipe, you know what the relationships are between these things in your head. And then you write out a recipe, and if the computer does it, then the outcome you desire happens. But you've lost, it's basically a lossy compression form to turn it into this imperative code, because The computer can't infer what you were trying to do with your recipe, right? You know mentally, like, I want to zip the things together, I want to map over that and multiply the two things, and then I want to reduce that by adding. But when you do it the other way, like, to get optimizations that you could get for not for free, but way easier if the relationships between these things were like actually still in the code, we end up spending man-centuries of like master-student time adding edge case optimizations to the Java virtual machine. Anyway, so what he found interesting about this is there's no implicit state required. A, B, and N don't appear. There are no variables. There's no assignment at all. It's hierarchical. It's constructed of functions that are composed together, and then 3 very simple functions using 2 sort of even simpler functions. And you can, as long as you're familiar with reading the style, you can understand what it's doing without really executing it mentally in your head. So it says what it's doing. It zips a couple of lists. It maps multiplication across them, and it reduces them with plus. The other code didn't read that way. You couldn't read the code and know for sure what it was. And you could figure it out, but it didn't just lay it out there for you. And it's not repetitive. It contains 3 steps. The previous thing contained n steps, so the size of the vector changed how many times you mutated data, right? This doesn't do that. So it's just better. It's fewer steps. It's easier to read. I know it's a loaded term to call this a more correct version of that function. I don't think this is actually a value judgment. I think it is like very clearly more correct. But that's up to you to decide. The fact remains, though, that here we're not describing a sequence of operations in recipe form. We're describing a relationship between these functions. And that is not lossy compression, right? We keep that. So we'll recap the things that are important here. There's no assignment. We're not concerning ourselves with the bookkeeping across the von Neumann bottleneck. At no point do we as programmers have to think about what variable holds what data, make sure we increment n, make sure we don't have an off by 1 error. None of that happens. We just describe the relationship that this function has with other functions. So you can't accidentally shadow a variable. You can't have your off by 1 errors. You can't have, with this one you can't have a division by 0 because it's not using division. Anyway, so I can almost guarantee that like shadowing a variable or overriding a variable accidentally or off by 1 errors have cost you or your employer money and time, whether you're aware of it or not. Because we described it the way we did, it's strictly composable. So we don't need to define a function that takes named arguments or anything like that. We can just like compose these functions, and that's the thing we have. Each of the individual bits are also composable. So if we want to build something that's very like inner product, but instead of multiplication, it has some other function, you just you use the first 2 bits, and then just change that sort of top piece. We don't have to fiddle with like dependency injection or plugin architectures or build this complex object factory to make things that are composable. And then we get back to the professor at the blackboard, because BACKUS spoke about being able to do algebra on programs, and this is really what he actually cared about. So being able to do higher order reasoning on our programs themselves. So here we've defined the function in terms of fundamental mathematical operations, and that's what you do algebra on already. So we can do algebra on this type of program. But if you have a recipe, right, imperative stuff I think of as a recipe. If I said to you, my goal is to do algebra on recipes, you would think that's the craziest freaking thing I've ever heard. And it shouldn't be, and that was his concern, right? You should be able to do, programming is math. We can do algebra on like mathematical structures. So why can't we do algebra on programs? And this was a concern of his in '77, and we're still basically doing the same thing. So that's it, basically. That's the reason that I think of this style as more correct, ultimately. So what's the point of the talk? There are 3 things that I want you to take away from the talk, and if you've been paying attention, you'll note that I've lied to you twice now, because I've changed the number of things I wanted you to take away. So how does it feel? How do y'all feel about that? Anyway, this is the real number, I swear. First, stop killing people. You have an obligation to build your software better. If we as a community don't take our obligation seriously, we're going to be in a world of hurt. So politicians will start regulating us, right? If we have essentially a bridge failure, we will have regulation of our industry. Or worse, we could be forced to write JavaScript. If you can come to grips with the naked, sheer cruel truth of my math, then you already know that you have an obligation to do stuff better. I think a great way to do stuff better would be to learn Elm or Elixir. Feel free to do it via DailyDrip, but that's up to you, murderer. And then secondly, give Elm a try. It's an amazing language. If you have not dealt with things like Haskell or something like that, it will change the way that you think. It'll also change the way you think about tooling, because its tooling is really, really good. The beginner experience is better than any other language I've ever used, which is good because I kind of vaguely knew Haskell. but not really. And now I know Haskell way better because I learned Elm. It'll also teach you that you can take some time up front and encode like the types in your system, like encode semantics into the types that make it impossible to ever have a certain state, right? Imagine you have the software equivalent of a bridge, right? And it, in some way, like if you had this off by one error, right, there'd be a problem, or the equivalent. So like I have another example that is in my talk tomorrow, but the point is you can build your type such that impossible states or states that would be really bad just can't be expressed in your types. And so you can't write code that would get you into the mess. As long as you encode stuff properly by thinking a little harder up front about your types, you can just type away edge cases. Like just they're gone. You never have to think about them again. This is really awesome. It'll give you confidence in your code that you don't have if you don't have a type system like this. Anyway, and finally, think functionally. It's still possible to write imperative code in most functional languages. You can't really do it in Elm, but it looks like you can. It does make it a lot harder to even have it look like you can, though. You can do it in Elixir. I often do write things that are more imperative in Elixir. I'm trying to get better. And then, so you can write less imperative style code. You can bolt on correctness, starting out with unit tests. Make sure you run them automatically every time you commit anything. You should have a CI server. Ideally, you should have a CI server that protects your master branch. We can't even merge code into our master branch unless it passes tests. So, and then you can add tooling like DIALYZER or QUICKCHECK or whatever the equivalents are in your language, and you can gain even more confidence in your code. So we can do better. We have an obligation to do better. So let's make the world suck a little less together. Thank you. Any questions? All righty then. Well, that is my talk.